So good time of the day, everyone. Welcome and thank you for joining the 98th webinar of the GIF Education and Training webinar series titled Overview and Update of the GIF Very High Temperature Reactors activities. So I'll start on the next slide with a few housekeeping slides. You should activate the sound to listen through your computer for the best quality. If you experience any technical difficulties, please look for the Zoom online support page. The most important part also to make this webinar as interactive as possible, and I will show soon how to do that. You can ask questions during the whole webinar, and the moderator and speaker will look and answer those questions at the end of the presentation. After the webinar, the recording will be made available on the GIF public website, so please share it with anyone who could not attend and might be interested in the topic of today's webinar. And at the end of the webinar, you will receive a survey to help us improve our webinars based on your feedback. So on the next slide, you can see that the Q&A option is at the bottom of your screen. So you should just click on the Q&A button and it will show a pop-up window where you can type your question and then send it. As I said, you can start sending questions during the webinar and we will take those questions at the end of the webinar. So Dr. Patricia Pavier will be moderating this webinar. She's the National Technical Director of the Molten Salt Reactor Program for the US Department of Energy at the Office of Nuclear Energy. And she has been an active member of the GIF Education and Training Working Group since the inception of the group. She was actually the first chair of this group, and she is now the webinar lead for the Education and Training Working Group. She has been instrumental in establishing the present series of webinars and keeps it flourishing for 97 episodes already with the energy and enthusiasm she puts in it. With that, Patricia, the floor is yours. Thank you.
Thank you very much, Alexeye. Good morning, good afternoon, good evening, everyone. I have the pleasure today to be here with Dr. Gerhard Swiedam, who is the Directorate Fellow at Idaho National Laboratory in the United States. He's also the National Technical Director for the United States Department of Energy Advanced Reactor Technology Gas-Cooled Reactor Campaign. He's responsible for overseeing the ART GCR program activities on graphite and high-temperature materials qualification, as well as GCR methods development and code validation. He represents the US DOE on the IAEA GCR Technical Working Group and the Gen 4 Expert Group since 2016. Until October 2024, he served for 4 years as the chair of the GIF Very High Temperature Reactor System Steering Committee. He is the author of more than 80 technical publications, including 53 journal and conference papers, and he received his PhD on the development of a multi-phase, multi-physics uncertainty assessment methodology for prismatic GCR in 2020. So without any further ado, thank you very much, Gerhard, for volunteering to give this webinar. I cannot wait to listen to your presentation. Thank you very much.
Thank you very much, Patricia, and thank you very much to our Generation 4 International Forum host today. Welcome everyone to this webinar on the VHTR system today. So here's an outline of what I plan to discuss today with everyone here. A quick overview of what we mean by the various acronyms with HTGRs, VHTRs, and so forth, a little bit of history. And then an overview of where we are with current deployment projects and test reactor projects and so forth, internationally speaking, of course. The third section of my presentation will be focused on what we do within the Generation 4 Forum, the collaborative R&D activities that we have, and I'll show a few examples of that. Okay, so let me start with this kind of layout of the 6th generation 4 systems as defined in the GIF. Here is a kind of a tongue-in-the-cheek slide asking, what do we mean by high temperature reactor really? If you look at the 6 systems here, you could argue that one of them is close to the traditional water-based reactors that's been around for decades now on the power generation side, but the other systems all run elevated high temperature outlets, right? Some higher than others. So arguably, 5 of these 6 systems are really classical high temperature reactors. So you'll see, of course, that there's many acronyms around VHTR versus HTGR versus gas-cooled reactor or even HTR. So if you want, you can classify high temperature reactors then as the general class of non-water cooled reactors that utilize either gas or liquid coolants, right? Of course, these can be fast or thermal spectrum reactors. So if you drill down into the gas-cooled reactors within this high-temperature group, there's several variants. The British advanced gas reactors, the so-called HTRs, had a lower temperature around 600 degrees Celsius. And of course, it wasn't TRISO filled. It's not TRISO filled. UO2 rods, it's CO2 cooled, and it had the graphite moderator, the rest of these systems as well. High-temperature gas-cooled reactor, HTGR, we usually these days refer to them with outlet temperatures, let's say below 950, but I add that little star there because depending who you talk to and what you read, some say above 750, some say above 100, some say above 1,000. But since both the Japanese reactor and some of the German test reactors operated at 950, let's draw a line at 950 for this discussion. So they characterized by TRISO fuel form and then mostly helium cooled. Some nitrogen has been suggested before as well. And then, of course, graphite moderator. So VHTR, the only real difference there is it targets the really high outlet temperatures, let's say above 950 C, 1,000 plus. And then GFR, a gas-cooled fast reactor, it is a similar system than the HTGRs, of course, less than 950 C. The fuel form is different, UO2 pellets in silicon carbide cladding. Helium cooled, of course, but as the name implies, it does not have the graphite moderator, right? So this is kind of the family overview. So in terms of VHTRs, people say, well, we don't have reactors currently being designed, that runs that high, above 1,000 or so. Well, we used to. Here's an example of the Utrecht experiment in the late 50s, 60s at Los Alamos. It was a small test reactor, helium cooled with graphite moderation, and it had a very high outlet temperature of 1,316 Celsius, high field temperatures, as you can see here on the slide. So it was successfully operated for about 11 years. It used highly enriched uranium carbide fuel, but it had some pretty advanced features for the time already with articulated contour rods, for example. The drawback, of course, is if you want to use these high temperatures, you cannot use the current alloys qualified for high temperature use under pressure. These do require refractory metal alloys at these elevated temperatures. So there are solutions to this, but it tends to be very expensive. On the right there, I show an example of space propulsion fuel being tested, TRISO fuel, in this case from the US company X Energy. So yes, we see very high temperature applications in the space domain coming up more and more these days as well. And these are obviously much smaller reactors. So why did generation 4 initially go for the V there in terms of very high? It also didn't exist back then. So 20 years ago, the idea was that we can utilize these very high temperatures mainly for hydrogen production. That's what started it in the beginning of this system arrangement. In the meanwhile, we've seen research and market assessments that tell us that, these lower outlet temperatures that we currently see in our domain, or anything between 700 to 950 C, this is really sufficient for many industrial applications. We really don't need the very high temperatures for many of these processes. And as I mentioned, we are limited by our current material challenges. If we want to do near-term deployments in the next few years, We really need to use some metallic alloys that's available to us in the various codes, for example, ASME here in the US. And we simply don't have materials that can tolerate, 1,000-degree outlet temperatures at this point without going into a refractory alloy domain. So here at the bottom table, I show an example of the ASME alloy 617. That is a kind of a newer high-temperature alloy available to the community, showing just a simple table here of at what pressures, how with higher temperatures, how the allowable stress limits is dependent on the pressure level as you go down, of course. Oh, and by the way, for the rest of this presentation, at the bottom, you will see many hyperlinks in terms of the sources where I felt that some additional reading would be good. So in terms of the history here, graphite moderated and gas-cooled systems are, of course, not new. The very first pile here in the US, Chicago, CP1, was a graphite system, air-cooled. Subsequently, in the 50s, both in France and in the UK, we saw the development of the Magnox and HTGR series reactors. As I mentioned, lower temperatures, around 600. These were CO2 cooled, but graphite moderated. So a lot of experience with graphite moderated and gas-cooled systems. We can trace the origin of pebble bed reactors actually way back to just after the Second World War. Farrington Daniels at Oak Ridge did the patent that you see here on the right in October 1145. So you see the pebble bed suggested here. The outlet, already helium cooled, was pretty high for the time, 732 Celsius. It used uranium carbide, uranium oxide in a cladding, so not a TRISO fuel form, but already a Brayton cycle. So again, if we think that, PBMR or pebble bed reactors or prismatic reactors are kind of new, being generation 4 advanced reactors, sometimes people get confused. This has really been done before. So this was followed in the 50s and 60s by experimental reactors. I show there on the top right the gas-cooled reactor experiment, GCRE. We had the mobile reactor ML1 here at the Idaho National Lab, site tested, EGCR, many of these, and you can, these are all on Wikipedia if you want to look them up. So the coated fuel particle idea started in around 57 with a combined UKAEA and Battelle idea back then. And it was subsequently then refined in the German program, of course, used in the pebble beds there. So particularly this fuel form is known for its superior retention due to that silicon carbide layer specifically at higher temperatures. And this is an older picture from the 1960s development era. So still staying with history a little bit, if we classify and see what's been around in the 60s, 70s, and 80s, you can basically split this between test reactors and prototype gas-cooled systems. So on the test side, you see the Dragon system in a Dragon reactor in the UK there, AVR in Germany, of course, the first pebble bed being tested, HTGR in Japan starting up late 90 and still operational today. And then, of course, the HTR-10 predecessor of the current HTR-PM system in China, the pebble bed reactor there. On the prototype side, we have one system in Germany, the THTR-300 that operated in the 80s. And the Peach Bottom and Fortson Rain facilities here in the US. The difference between these two test versus prototype is really that the prototypes were hooked up to the commercial grid, producing power, selling power, whereas the test systems are really meant for off-the-grid, non-commercial tests and operation. What I do want to lift out here is, if you look at the outlet temperatures, a few of them, HTTR and AVR were operated at high temperatures, 950 C outlets. And then in terms of the fuel, you see an interesting thorium mix entering here in terms of either coated particle or different fuel forms being tested. Specifically in AVR, had a lot of fuel tests on thorium, mixed fuel, thorium uranium fuel, carbides, oxides, and also BISO particles, which are just 2 layers, not the TRISO with 3 layers. So this shows the flexibility of our fuel cycle and the history that's been done before. So useful table this. So in terms of the current landscape, what we basically see are these two variants of high temperature gas-cooled reactors. Worldwide, there's either a uranium oxide or uranium carbide center particle, And that's, of course, coated then with pyrolytic carbon and then silicon carbide and another layer of pyrolytic carbon. So that gives us our tri-structural isotropic or TRISO fuel form. So if you go the pebble route, you can compact these within a pebble to form a pebble bed, or if you go the prismatic route, prismatic because it's a hex block here, as you can see from the geometry, you can, this is more like an assembly in an LWR equivalent if you want, and that gets packed into a fixed core, of course, like this for a prismatic reactor. So those were the bigger machines in terms of what we see right now in modular size. There's even smaller systems, of course, microreactors. Some of you might be aware that there's been a lot of developments, a lot of smaller companies maybe proposing new projects on this. So here in the USA, for example, I just compiled this table on companies currently working on small reactors. These are typically less than 20 megawatt electrical. It's not a real hard cutoff, but typically below 20 megawatt electric. You'll see different coolants there, but all of them are graphite moderated. And some of them are mobile, but not necessarily meant to be transported. So there's various options available here as well. So an interesting question comes up then, going from those small reactors, why currently all the small ones you saw on that table are prismatic designs. So why don't we see very small pebble beds? Well, maybe, and I'm just throwing a question out there for you to ponder, maybe there's a lower limit on size and power for a pebble bed reactor to still be economical and technically feasible. Maybe you don't want to deal with that moving fuel system for very small systems. On the other hand, do we think there's an upper limit to what HTGRs can do? Well, historically, General Atomics and the German program both looked at very large prismatic systems, 3 gigawatt systems, thermal. But if you still want the inherent safety and without any active cooling during loss of cooling events, then you really need a tall, slender core with or without a reflector. So we see that the limits, some papers have shown that maybe above 650, the temperatures during a loss of cooling event becomes pretty high. So currently we have a Framatome steam cool design out there. I'll show a slide later. That's around 625 megawatt thermal. On the pebble bed side, if you do not add a central reflector or annular core layout, you pretty much limit to around 250 megawatt maybe, again, based on how hot the core becomes during loss of cooling events. The PBMR 400 was a design above this, but that did have the central reflector there. So in terms of uses, then I mentioned space quickly in a previous slide. Here, other non-terrestrial uses on the right is an interesting design from a few years ago of a marine propulsion application for a pebble bed reactor. Not the normal randomly stacked pebble, but these are a so-called stacked pebble bed. So it's the fuel are constrained to flow down in fixed channels, but still horizontally orientated marine propulsion application. I thought that was pretty interesting. Again, the reference is there at the bottom. Okay, so some generic then properties of what we see in terms of balance of plant and the reactor. You see here on the right, this is just an example of the X-energy design. You see the properties in the table in terms of inlet and outlet temperatures and so forth. The helium flow path then, in case you're not familiar with it, rises up in the flow channels, enters the top of the pebble bed, flows down, and exits through this coaxial pipe. So this pipe or vessel really handles both the inlet and the outlet flow on the way to the steam generator then, which is located side by side, typically below the core, as opposed to some of the earlier designs that had the steam generator on top of the core. The Framatome steam-cooled MSCGR, the one I referred to previously, this is a smaller version of it. This is a 625, my apologies. Similar layout, of course, steam generator, reactor core here, just to show that it has about 102 fuel columns, 10 extra layers of them. So the rest of the properties are very similar to the pebble bed. So looking then at the basic safety design approach for our systems, the idea here is to use inherent material properties as a basis for safety, starting with the fuel really. On the coolant side, it's a single phase, neutronically transparent coolant, chemically inert, as you know, helium and the noble gases with a low heat capacity. The TRISO fuel particle is really the essence of the safety argument as a retention of fission products. Since it's a ceramic fuel form, it has high temperature capability, and the silicon carbide layer specifically has a high radionuclide retention factor. The graphite moderator, as opposed to water, has high temperature stability, large heat capacity, which really helps us a lot with transient events, and then slow, long thermal response times as well during these transient events. So in terms of inherent and passive safety features, then, again, the argument fundamentally within the safety case is most of the radionuclides are retained at the source, meaning within the fuel or the fuel compact. The shape and the size of our reactor designs are by design kind of tall and thin cores. The idea here is that you attain passive heat removal from the core using just conduction and radiation heat transfer, so fully passive events, in the case of a loss of force cooling. I'll show a picture in the next slide. It has, if you look at the moderator and fuel and total feedback coefficients, it's strongly negative over all conditions. So we really don't need a reliance on any AC power or side power or operator intervention even. And a little bit later, I will show that both the Chinese program and the Japanese program have demonstrated that loss of force of cooling events without intervention are successfully survived by this kind of design. And it really demonstrates the inherent safety of our type of reactor. So on the left here is a diagram from my colleague Frederick Reitzma, the IEA, that shows really the heat transfer mechanisms within, say, a pebble bed or a prismatic for that matter. There's a conduction effect, assuming you lose the gas flow, forced gas flow through the core. You will, of course, have some conduction, radiation, and remaining natural convection in the bed itself, but then conduction through the side reflector, and then purely radiation, some convection, but radiation really dominates for transfer between the core barrel, the vessel, and the reactor cavity cooling systems on the way to the concrete. On the right here is the behavior during our fuel temperature during a loss of force cooling event. You can see, first off, that the time scales are very long. The fuel temperature peaks around 180 to 120 hours, and then slowly falls away like that. Here in the US, our long-standing HTGR program has tested fuel up to 1800 degrees Celsius, for 300 hours, and we saw no appreciable UCO particle failures in our heating tests. We did, of course, see the movement of, for example, strontium, cesium, and europium, the fission products, out of the kernel layers and into the matrix, but no particle failures, as I mentioned there. So really a very robust fuel form with excellent fission product retention. This just shows schematically what I mean before in terms of what's the so-called functional containment. In traditional LWR space, you have the reactor building that's really meant as the retention function in case of the fuel melt or cladding breach. Whereas for our system, we really start with the fuel and make the argument that the layers, the coating layers, specifically silicon carbide, is really the first barriers and hold-up levels to fission product release. This goes for the matrix that it's embedded as well. So the functional containment then refers to the fuel form playing a primary role for fission product containment, if you want, as opposed to the building being credited for that. On the right here is a nice diagram that shows phenomena involved in fission transport, fission product transport, condensation, plate out, there's some dust generation, lift off, wash off. Each of these require their own kind of special studies areas almost. Okay, so that was a little bit of background. I want to dive into where we are today in terms of deployment projects. First off, let's take a little bit of a look of where we fit into the market. So on the left, I like this Sansky diagram from the Lawrence Livermore lab that they push out every few years. This one is from 23 for the US energy consumption. So it really just breaks up where and how energy flows from input to output and in terms of sources. So nuclear currently, as you're aware, flows fully into electricity generation. this red line here. What we would like to see, though, is we take over some real estate from, for example, natural gas or other sources, petroleum sources, where we think nuclear can play a much bigger role in industrial and even transport options. So in terms of, in terms of the integrated energy system opportunities, you can basically size the reactor gear to kind of fit what you have in mind at the end. If you add a thermal energy storage, like say molten salt storage in between, like Kairos Power is planning to, you even can decouple the reactor from the process heat side of the house. So, one of the major flow points here is that hydrogen is not only a product that can be made by high temperature systems, but it's also an energy carrier itself to produce a lot of these products that you see listed here on the right. So this just gives an idea, cement, ammonia, petroleum refining, mining, desalination. The uses here are really significant and on the chemical side, at least, very promising, I think. So here's an example of the planned project in Japan in terms of the current HTGR layout is shown here, the 30 megawatt reactor with an intermediate heat exchanger, 10 megawatt here, and that will be coupled to a hydrogen production facility a small distance away. The idea here is that you can use the flexibility of these cycles to, for example, as I mentioned, tap off from the IHX here, the hydrogen production line. You can keep on generating electricity to the grid via the gas turbine on this side. And in this diagram, from the recuperator side, you can, for example, hook that up to seawater desalination as well, which is a low heat application. So again, just shows the flexibility of what we can do if we have a high quality outlet temperature to play with. This slide here is from our colleagues over in the Gemini project. And it was presented this year in the summer school. This shows the size of the heat and hydrogen market in the EU. 7.8 megatons a year of hydrogen consumed in the EU. Most of this is captive, so it's directly consumed by refineries and fertilizer plants. We see that there's a lot of space in this market for heat transport, synthetic fuels, and then direct reduced iron processes. So the numbers currently shown it points to a generation of about 190 kilotons a year of hydrogen with a single HTR unit. So it's really promising in terms of what our reactor type can produce once it's hooked up to these industrial processes. The other use that I'm sure you're aware of, excuse me, at least in the US context, is talks that started between some of our members here and the data center community. On the right there is a kind of scary comparison of what electricity consumption of US tech companies compared to some countries. And it's pretty shocking to me, at least, to see just how much, just terawatt hours, companies like Google and Microsoft currently consume. And this is before the AI ramp really took off. This is 2023. It's comparable to several countries' total use. So clearly there's a use case here for nuclear in general to be hooked up to data centers in the US and Europe and elsewhere, of course. Two examples here in our field, Kairos Power and Google partnered to deploy about 500 megawatt of their designs. And then Amazon invested recently in X Energy, taking a stake of about 5 gigawatts of their reactors to partner with their data centers. So we'll see where this goes, but it's another development that's pretty recent in our field. Okay, in terms of projects in specific countries, I'll have a slide on each in the next few. In Canada, OPG, the utility there, and X Energy has had a framework agreement for some time now. Also in Saskatchewan, there's a picture here at the bottom. Saskatchewan Research Council and Westinghouse, eVinci, the heat pipe, the small heat pipe, had some funding announcements made earlier in late 2023. And you might recall that Global First Power and AutoSafe Nuclear got quite far on the CNL side, stage 3, if I recall correctly. with their licensing efforts there. USNC, in the meanwhile, was broken up into two different companies and brought out. So I'm not sure what's happening with these projects as such, but it might survive that takeover. On the right here, this is from my colleague Ali Siddiqui at CNL. He's the member for Canada on our VHTR System Steering Committee. His slide here highlights that Canada also started this new, what's called Nuclear Research Initiative. That really is an interface forum for many of the advanced reactor developers, shown there on the right. The goal there, similar to the US program, I would imagine, is to accelerate the deployment of SMRs and really make use of CNL's technical capabilities there to help that community as well. The other one, StarCore, is also moving ahead in Manitoba, one of the other provinces there. Late last year, there was an announcement that project is still ongoing then, just below 10 megawatt electric prismatic design. China, of course, has been a long-time player in this field with piggle-bed reactor designs. The HTR PM, the facility is shown here on the bottom left, has commenced commercial operations since December 2023. So those are 210 megawatt electrical units, more or less. They demonstrated district heating and hooked up to the local district heating for their local community in March 24. So they also did several tests to demonstrate inherent safety, right? So the total loss of the primary system cooling with no operator actions just showed the reactor shutting down by itself. And then their approach of using standardized designs and a balance of plant approach, designing and then copying and pasting the various turbines and steam generators site to site, that shows the economies of scale and site flexibility. Again, a reminder that at the bottom, I have a reference source for these slides that you see, in this case from our colleague, Professor Li Fu at INET, which is the member on the SSC. So next up for China is then the HTR PM600. So as you can see from the diagram here, this is a 6-unit system. You see the piggle beds there in clusters of 2 hooked up to central services. So the idea here is that you would eventually then couple such a design, the HTR PM600, for steam and electricity use. So the Chinese government approved this 6-module plan design in August 2024. So that will go ahead, and design with this is already really advanced. The next scale up from that is to add a 1 gigawatt class light water cooled reactor at the same site and couple it with the units here so that you really have a very flexible mixed reactor application and facility that can do cogeneration at one site. So really ambitious targets here, and looking forward to see what happens here in the next couple of years. On the Euratom side, both within the Gemini project and then in Poland, there's been quite a lot of activities. Europe is aggressively targeting the process heat side of the equation, looking at hydrogen applications. So under the Gemini 4 project, the cogeneration of steam and hydrogen is a large focus area. Recently, they've refined some of the design aspects of this first design, reactor design here, shown at the bottom left. The HTGR Polar project in Poland is pretty far along with the preliminary safety report at this point on the basic design. This reactor design, the idea here is that becomes the basis for the commercial HTGR reactors in the Polish industry. And there's a huge market here. The 15 largest Polish chemical plants require 6.5 gigawatt of thermal power in the form of steam. So the community here, our community colleagues in the EU, feel that there's a lot of potential for this technology in the European market. So in the next few phases, they will continue their work and end up with their detailed technical design in about 2 years, licensing, construction, and then commissioning. So hopefully in early 2030s, this project will be successful. In Japan, I mentioned that the HTGR, the high temperature test reactor, was one of the systems I showed before. It's been operational since the late 90s. They demonstrated in a series of tests, 3 of them, a full stop or full loss of forced cooling, if you want, stop the helium flow completely without scram, so without operator intervention. And this was measured as part of a demonstration of inherent safety. It's also an NEA benchmark now that we participate in, for example. So you could see the flow rate and power behavior here at the right. It will go, it went recritical a little bit later. That's not shown on this plot here, at very low power levels, and then the rods was inserted. So just to demonstrate how inherently safe this design is, really. An excellent data set for validation of our codes as well. Staying with Japan, next up for them after the HTGR test reactor has been deployed already there is the largest system in the 150, 200 megawatt, 250 megawatt range, prismatic, of course. The idea here is, again, hydrogen production. So they show the technology roadmap there in terms of the timeline for their development plans. This is from our Japanese member on the VHTR SSC. Mitsubishi Heavy Industries were awarded more or less eventually total $3 billion of funding as a prime contractor, and it will take care of most aspects of this upcoming project then. So again, another process, hydrogen-focused project coming up online in Japan, hopefully within the next 5 to 8 years. Republic of Korea also announced in, I think, July 2024, in summer last year, they allocated some funding to develop a prismatic design by 2027. This is a great example of public-private partnerships. We have something similar here in the US between the US DOE and private companies as well, where funding flows in a joint manner. So in this case, Kerry will then design the nuclear reactor itself, while the 5 industrial partners will do the balance of plant and the application side. So in this case, we see, for example, that POSCO plans to use it for their steelmaking facilities, SK Ecoplant for water electrolysis, hydrogen production, and then Lotte Chemical for the petrochemical business. So right from the beginning, this project is planned to use process applications not as opposed to electricity, but in addition to electricity production. The UK has seen a lot of activities picking up as well in this domain. For example, a collaboration with JEA is ongoing between the UK, Poland, and JEA to accelerate the deployment of gas-cooled systems in the UK. The UK government declared that they want to see a demonstration HTGR operational in the early 2030s. On the UK side, the National Nuclear Laboratory, the NNL, and JEA are along with what's called front-end engineering design, FEED. You see the layout there. And NNL also selected Jacobs to review the initial designs and the plans in May last year. So this project is making good progress as well. On the right, without fuel, there is not much of a reactor, of course. So the UK also launched investments into a coated particle fuel program in conjunction with this demonstration reactor. So again, NNL was awarded the contract for this step 1. And then JEA continued their collaboration there in terms of a memorandum for fuel manufacturing technology. So the idea here is that NNL will take the role as an integrator of this fuel development program, which will carry out research and development and prototype development for the first prototype fuel block, coming in, hopefully still being on time for later this year. In the US, a lot of activities. I alluded to some of them before. The Pebble Bed reactor project from X Energy, the XE100, is still being planned for Dow Chemicals facility in Seadrift, Texas. Planned operation still for 2029 at this point. So 4 units being deployed there to supply steam to Dow Chemicals, chemical and industrial processes there. Kairos Power, although a fluoride-cooled system, is graphite moderated TRISO fueled, so I included that here. It is they received approval in July last year to start construction on their Hermes test reactor. That's a 35 megawatt unit. It is really significant. It was the first non-water-cooled reactor approved for construction in the US in more than 50 years. So real milestone for our community there. The commercial units that will follow this Hermes 2 are 2 units hooked up with an intermediate liquid sodium loop and a common power conversion. It will be at the same site in Oak Ridge. On the right there, I show the dome facility here at Idaho National Lab. It is our old repurposed EBR2 reactor dome. We will test some of these vendors' microreactor designs in dome. So the first up will be Radiant and Westinghouse that were awarded DOE funding for front-end engineering experimental designs of their TRISO system. So we're looking forward for that to come online as well. So this timeline you might have seen before. We typically show that here at Idaho National Lab to lay out the projects coming down the line. I just mentioned the ones here that the front-end engineering has started in terms of fitting these small reactors one by one after the other, into the dome for testing. We also have the Project Pele here, which is a mobile prismatic test reactor. And then the Hermes, sorry, let me go back. My mouse is messing around with me. Hermes and Hermes 2 shown on this timeline here in terms of when they plan to deploy, and X-Energy on the timeline here. So the point being that between BWXT, X-Energy, Kairos, and then formerly USNC, we had quite a few of these TRISO graphite systems under development in the US. Okay, so that was a quick overview of where we are with deployment projects. Let me dive a little bit then more on today's topic for examples, a few examples of what we do within the Generation 4 Forum on HTGR systems. So this is what our system and project arrangement looks like. How this works is the country members sign on to what's called the system arrangement. That's the overall umbrella, and we have 10 country members currently signed on. And within that, there are 4 project arrangements, basically detailing how we will do the collaborative research work. In our case, we have the materials, fuel and fuel cycle, hydrogen production, and then computational methods validation and benchmarking project arrangements. So these 4. And I will provide, I think, 2 slides on each of them to give you an idea of what we do in these groups. So just a slide here to bring the point home that, you know, if it's graphite or TRISO, it doesn't matter. We follow similar steps in terms of what we are focusing our research on. There's a lot of activities early on fabrication. How do you make these things? At some point after you've characterized the baseline, you do want to irradiate this in a reactor facility of some kind to see what happens with it, of course, under irradiation. You then do various testing on it, can be safety testing as well, post-irradiation. The idea would then be to transfer to a hot cell where you do post-irradiation examination, PIE. You need to understand what happens to the materials and how they behaved under these conditions, of course. And then all throughout the cycle, and then at the end as well, modeling and simulation, of course, predictive, and then for validation using the actual data is all around this, right? So you'll see research focused on materials issues and then applications and modeling and simulation. So if you look at the materials PMB, here's an example of a really excellent case of collaborative work within this community. There is a database for graphites, composites, and metallic alloys. It's called the VHTR Materials Handbook. So the handbook there is from back in the day when it was actually still an actual handbook. And now it's a database, of course. It was or it is at Oak Ridge National Lab for a long time. We are transitioning this to the Idaho National Lab right now. I show here on the bottom left table of just showing what the members contributed so far in terms of actual R&D reports. So these are actual entries, actual data sets of these materials into a database. This is, you can request this data on the website. I list the link there. Our handbook point of contact there is Courtney Otani at Idaho National Lab. So there's a whole procedure laid out. So it depends on, you know, the signatory member, your relationship, if you're a commercial company, with your signatory member. For example, in our case, you know, what is the relationship between X-Energy and the Department of Energy, and so forth. So there's several criteria for you to qualify to get access to this. But the idea is, of course, that this very valuable resource is shared with the community. In terms of one of the tasks currently ongoing, I picked an example here from the Korean group, from the Korean member in the metallics and design methods area. This is a plot here of the fusion welded alloy 617 creep rupture. So it shows the time to rupture of the diffusion weldment compared to that of the received alloy. So, at various temperatures. So if you go from 800 to 950 C, you can see the time to rupture then, of course, being a function of temperature. So typically this data is what would be taken up into the materials handbook. On the fuel and fuel cycle side, two examples here of what we're currently working on, for example. Just examples, there are many other tasks. China has been looking at the older HTR10 spheres now that these are available from the reactor operation. So those spheres have been deconsolidated and looked at burn-up analysis of that. There's also investigation into the high temperature annealing of silicon carbide. So to what degree does silicon carbide then anneal under high temperatures to see what happens with the microstructure? There's been several attempts or several focus studies on zirconium carbide coating layers to see how that, at very high temperatures, 2200 Celsius in this case, to see how that could improve performance. So right now, the Chinese team reported that at HTR PM, they just under 1.2 million fuel pebbles already made. The first load fuel, of course, has been completed, and they started with the equilibrium fuel 8.5% specified fuel fabrication. On the right, there's been an uptick on HTGR activities in France as well. You might recall France is primarily invested in fast reactor systems and water-based systems. So HTGRs has not been their primary focus for a number of decades now. But there's been a few more smaller startups in France recently. So CEA has started to divert some resources on that for support. There's more interest these days in TRISO fuel activities there as well. For example, fuel modeling activities as part of the next work package with the Atlas code that they have in CEA. Another example here, it's still staying with fuel and fuel cycle. I mentioned the HTGR Polar project. Again, on the fuel side, you need to, in parallel, not only develop the reactor design, but also the fuel. So there is an activity here with to set up an advanced TRISO lab. Lab scale production rates of about 2 to 3 kilograms a day. So obviously not commercial at this point. The mission of this laboratory is to establish a fuel development fabrication capability and then do the full characterization, irradiation, and PIE cycle of that fuel. In the US, we've had our long-running AGR TRISO experimental program here. It's almost 2 decades old now. So we're finishing up the final AGR 567 irradiation experiments, PIE, this year and next. And the high temperature safety testing up to 1800 degrees Celsius is currently in progress as well. The earlier test series, AGR 3-4, that PIE is now completed, and we're collecting the data for dissemination. This will specifically be very helpful for fission product transport codes when this data set becomes available. Next up here for us in the US side is development of our air and moisture ingress testing capability. So we have a facility where we heat up the fuel and we want to ingress a mixture of air and water in that cell, hot cell with irradiated fuel to see what happens with oxidation effects. We hope that will kick off later in 2025. On the hydrogen side, 2 examples here from Canada and EU and France. On the Canadian side, CNL is making significant progress with co-electrolysis demonstration at a cement production facility in St. Mary's. And on the EU side, they're looking at the progress on the hybrid sulfur cycle. They have a couple of demonstration projects, so scaling up happening right now in the 0.5 megawatt range, where they partner with industrial companies such as Grillo in Germany, which is a key player in sulfuric acid manufacturing and recycling. So again, a very nice connection to the chemical industry here being explored. So in France, the largest high temperature steam electrolysis electrolyzer installed in an industrial environment is ready to start. That capacity there, 60 kilograms hydrogen per hour, it's a 2.6 megawatt electric facility there. So the picture is shown here at the bottom right. So again, good progress there in terms of looking at hydrogen and other processes for high quality heat. In the UK, the focus is also on high temperature steam electrolysis, more on the modeling and technologies at this point, and also reaching out to industry to make sure what the end user needs are. It's important to note that you also need to figure out a regulatory environment. Different regulators control nuclear and chemical facilities, for example. How do you interface on that? You also need development of some codes and standards for hooking up nuclear with chemical facilities. So a lot of activities in the UK focused on that as well. Here in the US, at the overall, we are focusing on the same technology, high temperature steam electrolysis. We have a large program, H2New it's called, run on improving cell performance and durability and improving operating conditions. At INL, there's what we call the Energy Technology Proving Ground. The development, the site just started here, a picture at the bottom right. We're setting up a scale facility, hydrogen production and post-processing scale facility there, where we want to demonstrate industrial scale hydrogen and synthetic fuel production coming online by the late 2020s. So we're looking forward to that as well. Right, and then the final example I have here is from our computational methods validation and benchmarking group, CMVB. As the name says, this is all about code development, code validation, and so forth. Here's an example of task 2.2. One of our contributions there is looking back to the HTR10 outlet plenum mixing. So this is a challenging problem. These outlet plenums in the pivotal reactors are pretty complex. So the CFD approach here is important, how you model this, what assumptions are made between, for example, LES and RANS. If you're a CFD person, you would recognize the acronyms. The idea here is that collaboratively, we work on the benchmark, the other partners work on the benchmark, and we start comparing results at some point. Another example here from Canada's contribution. Last year, they spent some time year before on looking on phenomenal ranking tables, PERTs, for gas-cooled reactors, and they presented that the results at the G4SR5 conference last year as well. Canada, CNL specifically, is a significant participant in the high temperature test facility benchmark. It's an OEC benchmark now of the old Oregon State facility, the HTGF. So the Canadian team are participating there with both system codes and CFD codes. And then on the last bullet here, another collaboration example. The Griffin code is a NEAMS code supported by the DOE here in the US for neutronics, and CNL was or is now licensed and the user of the Griffin code. So, another example of how country members collaborate and share tool use and compare results for the same facilities. On the right is an example of what Japan is looking at modeling our ATR reactor here at INL. You recognize, some of you might recognize the serpentine fuel shape here of the ATR with drums. It's a very complex benchmark. We had our AGR fuel in this facility, of course, being irradiated. So we have very high fidelity data benchmark here on the burn-up involvement of AGR fuel particles, TRISO fuel particles, and it's an NEA benchmark now as well, or it will soon be, put it like that. So the Japanese team has made significant progress in modeling this, and we will be comparing results soon with them. Okay, so the final slide I have here in terms of our activities, if we look a little bit outwards, we also have interface roles. Several of our members act on other committees and other interfaces as well. For example, with IAEA, we participate in several technical working groups. There's a bunch of hyperlinks and explanations of all the acronyms here at the bottom that I won't cover now. But we see similar expertise and similar faces on many of the OECD, IAEA, and Generation 4 expert group meetings, for example. So there's a lot of synergy already between these various activities. The second bullet there is when you look back at what the current NECA working group is, so that stands for non-electric and cogeneration applications of nuclear energy. It's a working group within Gen 4 now. From the very beginning, the VHTR system was instrumental on that work of energy system integration that I showed in one of my slides. So we've been always, as our initial target of hydrogen production was back in the day, being involved in this application. On the proliferation side and safety side, we've worked internally with the Risk and Safety Working Group and also the Proliferation Resistant Group here, PRPP. We did a joint white paper on non-proliferation safety, with them a system design criteria publication as well. And currently we are involved with both these groups on a 3S by design, so safety, security and safeguards with these groups. So looking forward to see that working as well. On the waste side, both for fuel and graphite, that activity for fuel is currently included in the scope of the fuel and fuel cycle PMB, but we don't have a lot of activities yet. Euratom is making some progress within the carbo waste project on this topic, and there's an HTR paper here below from where I grabbed the very nice pictures on the right as well. So there are solutions to reduce the volumes, for example, significantly of TRISO fuel, which is one of our regular critique points. So this full report on this Gemini 4 waste options for that design will be available by the end of this month, I believe Michael Futura said. So just a flavor, a bit of an overview of other interfaces and activities we have outside the direct PMBs. Okay, I want to end my presentation then with a couple more resources. Obviously, I needed to highlight the Gen 4 link there at the top, but just a few more generic links and overview papers. There's, of course, much more than this. So just in case you are interested for more reading as well. Okay, and I think that concludes my discussion. Thank you very much.
Thank you very much, Gerhard, for this very comprehensive presentation with a lot of participants. So while you take a small break before the questions, I'm going to invite the people for the next 3 webinars. If you're interested, on the 27th of March, we will have Marta Gospodarczyk from the IAEA. Will present nuclear power, electricity, and beyond the grid, data-driven insights from the IAEA Power Reactor Information System. On the 15th of April, Isabella van Rooyen from PNNL in the United States will present advanced manufacturing supporting Gen 4 reactor system. And on the 14th of May, we will have our IAEA GIF joint webinar with advanced nuclear technologies for maritime application. And this is the IAEA this year will organize the meeting. So stay tuned, the 27th of March and the 15th of April webinars. The link is already available on the GIF portal. Next slide, please. I would like also to mention our initiative in the Education and Training Working Group, which is the 2025 Pitch Your Gen 4 Research Competition. We have opened on the 1st of October a call for executive summary. We are trying to target PhD students, postdoctoral fellow, and junior engineer with a PhD that are working on Gen 4 nuclear energy system to put an abstract. And we have a jury. We will select between 10 to 15 abstracts. These juniors will have an opportunity to pitch their research in a video, 3 to 4 minutes. And the winners will be invited to participate in a GIF event, as well as presenting a webinar on the topics of their research. So I'm asking each one of you, and you are around 100, to really pass on this information. I really would love to have all these students and postdoc and juniors participating. You have the link, and it's pretty easy to go on the GIF portal and to find this research competition. So without any further ado, Gerhard, I'm looking at the Q&A chat box. We have 7 questions for you, and I don't know if you can see them as well.
I can see them. Yep,
okay,
I can
very
see them.
nice. Very nice. So I'm going to start with the first one. It's worth noting here that for thermochemical hydrogen production, the conversion efficiency at 1000 degrees Celsius is 3 times that at 750 degrees Celsius. So it was a comment. Thank you very much. The second question that I see, thank you. I would like to get more information on the Polish fuel R&D project. What type of fuel, TRISO, uranium dioxide, and when is it available?
Thank you, Didier, for the question. Unfortunately, I don't have more information on that myself. I will, in the slide where I talked about the Polar project, our European members contact, Euratom member, Michael Futterer, was indicated. So I think Michael would be able to answer that for you, or at least get you in contact with the Polish team here. So my apologies, I'm not sure what exactly the fuel form is. It will be UO2. I'm pretty sure it's not UCO, but the exact information data set, please contact Michael Futterer. His email is in that slide.
Thank you very much, Gerhard. Next question, will NGNP projects continue in the future?
So the answer to that is no. The US Congress ended the NGNP project formally in 2012. It was, however, continued in the form of the current program that I'm leading, the Advanced Reactor Gas-Cooled campaign. So the fuel and the graphite characterization did continue, and the methods development. So yes, it continued under another name, but not as NGNP. Your second question, Patricia, I'll just read that. How can we predict and control core bypass flow? That's a challenging research aspect currently still. Some teams have been, for example, X-Energy or the Chinese HRPM team, might find it easier to assume some bounding conditions, 15%, in lieu of more detailed characterization. But it's been an outstanding issue for our community for a while. The gaps between the blocks are very small, the designs are very large. So to throw full house CFD on that is maybe not feasible everywhere in the reactor. We know the engineered flows in some of these channels pretty well, for example, control rod flow. But it's maybe easier at this point to be a little bit conservative and say, let's assume, X, 10%, 15%, 17% is bypassing the core, and we see what that does to our margins. But it is a challenging modeling and simulation project, and there's a few small experiments I'm aware in the US, for example, maybe in China. But you're right, it's one of our complex and challenging problems.
Thank you, Gerhard. Next question. It's moving. What is your opinion on the use of UO2 versus UCO and on their fabrication difficulty? Is UCO more problematic?
Again, a tricky one for me, Didier. I'm not a fuel specialist myself. If there's pros and cons, I think, to both of them. Not so much on fabrication difficulty that I'm aware of. I mean, they have slightly different processes, but I wouldn't say the one is significantly more difficult than the other. Different metallic fission products, for example, palladium or silver, might interact with these two fuel forms differently. And also, UO2 might produce different products that is maybe problematic for silicon carbide, for example, than UCO does. So again, pros and cons to both. We have a lot of experience on UO2. No one else outside the US is currently using UCO that I'm aware of. But the UCO fuel form was designed to take care of some of the UO2 effects that we saw in the past, and maybe to allow slightly higher temperatures as well on fission product side. I would advise or recommend that you contact Paul Demkowitz. He is the FFC chair right now in our system, and his detail is in one of those slides where I mentioned FFC. He will have a 5-page answer to your question that I cannot supply here. So thanks for that, Didier.
Thank you very much, Gerhard. Next question. What are the main technical challenges for VHTR materials, equipment, such as IHX?
Yes, yes, indeed. Good question. So if you want to go up that high in temperature, the core barrel, the vessel, the steam generator design, the IHXs, it all depends on the cycle, of course, but it all that gets stressed under high temperatures like that. So I would say yes, your focus there is correct. It is mainly a materials challenge. It's not a reactor challenge, right? It's really, do we have the materials qualified and tested and even taken into the ASME codes, right? For example, in the US, you cannot use a material in a design if it's not certified, codified by ASME. So not only do you need the data, but it needs to be actually taken up into the code itself. So you're right, it is material challenges, metallics specifically, that's keeping us from rising really high. But as I mentioned in my slide, if you want to use refractory metals for space applications, you can do that. It's just much more expensive.
Thank you. Next question. What are the reasons for selecting silicon carbide, zirconium carbide as coating for TRISO fuel?
Yes, excellent question. So these coatings, these specific silicon carbide layers specifically, was introduced. Initially, they were just pyrocarbon layers. So later in the development of fuel, it was recognized that silicon carbide specifically is excellent at retaining some of the metallic fuel products as well. So it plays actually the primary retention factor in TRISO fuel. So if you take those layers away, you will lose a lot of the retention capability. So they are very important. They have high stability, and the way they chemically interact as well with some of the fission products is important, specifically the metallics. Zirconium carbide is another option as opposed to silicon carbide. There's been a lot of research on that lately. I'm not too familiar, as not being a fuels guy, on what the advantages of zirconium or silicon would be specifically. It can probably compete better or perform better with some metallic fission products, but there will always be trade-offs, right, between the two. So just suffice to say, there are plenty of research currently going on both of these.
Thank you. What is the fundamental lower size limit for an HTG microreactor before neutron leakage makes it impractical? Are there any theoretical ways to push this boundary further?
Well, if you think about reactor physics here, as long as you keep on using graphite, this core will be leaky, right? It will scatter a lot, it will leak a lot. So you either change up the moderator, moderated by something else than graphite maybe, or you think about reflection back into the core maybe on the edges of the small core. I mean, from the fuel form, you can't do much about the way neutrons is produced. But what you surround that fuel form with can maybe improve things for you, right? So as I say, I don't want to specify a specific, moderator or reflector here, but some of you might be thinking where I'm going with this. If you take away the graphite and put something else there, that's a better moderator or reflector. That will keep your core size small, and you won't have as much leakage.
Thank you, Gerhard. The next one, can spent TRISO fuel be reprocessed to generate MOX fuel, or must spent TRISO fuel be sent for disposal?
Right. So that's another active area of research in various countries right now in terms of disposal options. A few countries I think I'm aware of in the past looked at reprocessing TRISO fuel, but not as many as just looking at disposal options. I'm not sure. Patricia, I don't know if
yes,
you...
and thank you for asking me, because I wanted to jump in, as my expertise is also on reprocessing. This is stupid. You should not reprocess TRISO fuel. It has been created actually as a very robust material, a robust fuel. We have tried, I remember at Idaho National Laboratory, we have tried to crack the TRISO fuel and really the layers in a microwave. We can, definitely. But then you have to think to upscaling and cost. Does it make sense to try to reprocess a TRISO fuel? No, it doesn't make sense. So that's my answer.
Excellent. And I think we can, Michael Futter has mentioned that we can, reduce the volume of TRISO fuel. That surrounding matrix can be reduced by orders of magnitude, right? So there are ways. It's a very robust fuel form, as Patricia said, but that does not mean it's impossible to then, decrease the volume by taking away the matrix again at the end. So there's a lot of research there as well.
Next slide. Why are the safety limits different between lower 650 megawatt thermal for block type and lower 250 megawatt thermal for pebble bed?
Yeah, so small correction there. If you want to compare the two directly, the 625 design from Framatome has a central reflector, so it's an annular core, right? And the 400 megawatt pebble bed also had the central reflector. So the 250 was for a cylindrical bed, right? You cannot remove the heat from the center of that bed if it gets much bigger. So if you want to compare the two pebble beds and prismatic, say 400 and 650, interesting question. Maybe it has to do with the way that flow channels are defined. You have actual flow channels in the prismatic blocks surrounding the fuel compacts, whereas for a pebble, you have the porous media flow with the central fuel kernels maybe getting a little bit hot if you go much above 400. I've not seen designs for 600 megawatt pebble beds, for example. So my guess would be that those fuel temperatures do get too high during a loss of force cooling, whereas for your prismatic designs, maybe the heat removal is better through the prismatic blocks, and that sets up the temperature better. But it's an interesting question. Good point.
Thank you. Is there any work research aimed at experimental validation of the modeling efforts that are being pursued?
Yes, there's a lot of activity ongoing in our CMVB project arrangement, as I mentioned. The problem is usually that the funding organization initially has first rights or locks it up for a while for their own purposes, right? If you paid for it, your team gets to use it first. So we find here and at IEA and at OECD that it takes a while for these validation data sets to be disseminated to the community in a form that everyone can have access to it. For example, the HTR PM team in China is involved within our CMVB to produce a benchmark for this first startup physics of their reactor. And that is very, very important to the community, of course, as you can imagine. But it takes time to set up that benchmark. They, of course, use the data internally as well. So it will take some time for it to be released outside for use by others. So yes, in answer to your question, there's actually a lot of experimental validation ongoing, but it takes time to be reached to the public domain.
Thank you, Gerhard. Do all HTGRs use a steam generator and Rankine cycles for electricity generation? Would there be any benefit to using a direct Brayton cycle?
Yes, it would be. I mean, the efficiency of that cycle will be much higher. And indeed, the PBMR company in South Africa way back did look at a direct Brayton. The problem there was, technological challenges like magnetic bearings, or how the seals perform at high outlet temperatures of maybe 900 C. So it wasn't really a question of can you do it? It can be done. But having a direct turbine of that size was problematic at that point. The cost is maybe a bit high. Some of the smaller systems would definitely benefit by using a direct Brayton, I would think. Gas turbine technology are really advanced in the aviation industry, for example. So there's a lot of promise that the Brayton can be implemented. Right now, no one is using actively in the next couple of years anything else than Rankine cycles. But the Brayton has a lot of promise for future use.
Thank you. And we have a comment from Michael Futterer. Yes, you can reprocess you can crack the particles and then dissolve the fuel in nitric acid. But if it makes economic sense, is a matter of local waste cost in particular. And feel free to contact Michael. I think his email address is on one of Gerhard's slides.
Yes, that's correct. Thank you, Michael.
Okay, very good. Thank you, Michael. The next slide is TRISO fuel sufficiently qualified to be used in SMR such as XE100? If not, what is the critical step to support the deployment of SMR in the near future?
Yes, excellent question. In the US context, you mentioned XE100 here. There has been, based on the more than 20-year efforts from the DOE labs here, DOE funding at ANL, for example, and Oak Ridge, we have a lot of data on how UCO performs. So in 2019, we set up a large white paper and interacted with the NRC, our regulator, on the status of TRISO fuel qualification in the US. The NRC was subsequently very supportive of that white paper. My understanding is that our companies here, X-Energy, Kairos, BWXT, they are all using that white paper to great success with the NRC in their discussions and with DOE to show that there's a good basis here for qualification. So I think in the US context, we probably would need to finish the program in terms of the series of tests that I mentioned in the next couple of years. But I think we're at a good point where there's no additional work probably needed as long as you stay within, let's call it, a certain envelope around that fuel. If you tested the fuel to 15.5%, with a high burn up and at certain temperature, you probably cannot easily apply that to, double the temperature and double the burn up, if you see my point. So if you have a case in mind where you're going to stress a fuel more, either in burn up or temperature, you're moving off that validation basis maybe, or qualification basis, and you would probably need to justify to the regulator then why you think your fuel is still okay. So that's an argument for the commercial vendors to make then. Also in China, of course, since they have an actual operating pebble bed reactor, and they had the HTR10, Japan the same, there's examples of TRISO fuel being operated right now in those countries. So clearly, then it is ready. Country to country, then of course, you'll need to go through similar steps to qualify your fuel in the UK, in Poland, and so forth. You can leverage maybe the international experience, but at the end of the day, you will have to qualify the fuel that you fabricate.
Mm-hmm. Yeah, very, very, very good. Very good question. Very good answer. Another question: how well do Monte Carlo neutron transport simulation capture the behavior of pebble bed movement, fuel shuffling, and localized burn-up effects? Are there fundamental uncertainties that limit predictive accuracy?
I mean, there are. You're aware, of course, if you're an electronics person, that, cross-section uncertainties will always be with us. So, even with Monte Carlo, we're always dependent on the NDF libraries. So that will stay there. I mean, we hook up Monte Carlo, high-fidelity Monte Carlo these days, with DEM codes that simulate movement. We can do very detailed, snapshots of the core of big regions, if not the full core. Can we drill down to the full core with all the TRISOs being taken into account? I mean, approximately, yes, we're pretty good with that already, but there will be, assumptions and uncertainties here. Oak Ridge Lab has done a lot of work with the shift code, if you want to look into that. And also the Griffin code here at INL, for example, has done, combined shuffling and high fidelity physics. So I think localized burn-ups, these kind of effects have been pretty reasonably captured. We made a real good progress in this in the last 5 to 7 years, I would say. If you're, however, a multi-physics person, if you're an electronics guy, you will worry about your uncertainties. The uncertainties on the thermal fluids, on how gas flows, on heat removal, on radiation transfer outside the core, those are much bigger than electronics. And then you add fuel performance uncertainties on the fusion factors, right? When you get to fuel performance codes, those are even bigger than the thermal fluid uncertainty. So if you pull out far enough, I have to say here, unfortunately, if you're a physics guy, that the uncertainties in the physics side of the equation is really swamped by other much larger uncertainties later on. So a few of us are not too worried about the remaining uncertainties in neutronics, if I can be, high level on that. I hope that helped.
Thank you. Thank you very much. I do not see any other questions in the chat box. So we got 17 comments and questions. I would like to thank first Gerhard for really answering. I'm amazed by the breadth of your knowledge. Gerhard, thank you very much. I would like to thank also the audience. After almost an hour and a half, we still have 83 attendees. I would like to thank these attendees to really be active and participate, asking questions. I think that's the goal. As you know, these webinars are all archived, so they will be available very soon on the GIF portal, as well as on our YouTube Education and Training Working Group channel and the Bilibili, because China cannot receive YouTube. So Bilibili will have also this presentation on the Education and Training Working Group channel. So with luck, I invite you, if you have time, to join us again on the 27th of March for our next GIF webinar. Thank you again, Gerhard, for volunteering to give this webinar. It was a great presentation and great session, Q&A. With that, I thank you, everyone. I wish you a good day, a good night, a good afternoon. Thank you. Bye-bye, everyone. Bye.
Goodbye. Bye-bye.